Hi everybody, this is our lecture on section 6.5, curl and divergence. So this section is kind of technical, and it may seem like a little bit pointless at this point, but you'll see what it's for later in sections, not 6.6, but 6.7 and 6.8, although it's introduced now. So define, and we've used this thing before, this gradient operator. So it's the three-dimensional vector with differential operators partial x, partial with respect to y, and partial with respect to z. So now the divergence is defined as follows. Given a vector field, 3D vector field, F equal to P, Q, R, like that. So only for three-dimensional vector fields. The divergence of the vector field F is equal to, well, it's the gradient operator dot F. So that is partial with respect to x. So it's partial with respect to x, partial with respect to y, partial with respect to z, dot p, q, r, which in the end becomes what? Partial with respect to x of p, plus partial with respect to x times q, plus partial with respect to x times r, which in the end is just px plus q, partial derivative of q with respect to y, plus partial derivative of r with respect to z. So for example, given the vector field equal to y plus x, 3y minus x, z squared, the divergence of f is just the derivative of this with respect to x, the x component, 1, the derivative of the y component with respect to y, 3, plus the derivative of the z component with respect to z, 2z. So you just get 4 plus 2z. And notice the divergence of f is a scalar function. Okay? Another thing that you can do also, calculate the divergence at a given point at the point 1 to 1 or something like that, and that's going to be 1 to 1. So that's just equal to this. At 1 is 4 plus 2 is 6. Now you may be wondering, what is the meaning of divergence? There's various attempts at in the section in the book as to what divergence means. But unfortunately, they all just kind of fall short and seem kind of odd to me when they talk about them because, well, what does it really mean? Is its meaning in the divergence theorem. So the meaning of the divergence of vector field F, will be revealed in section 6.8 on the divergence theorem. In some sense, what does it mean? given a region, like a closed sort of globular region in three-dimensional space, how much of the vector field is flowing out of that closed space, right? So sort of flowing out from nothing. So how much production of energy is coming out of that closed space? So that's what's measured by divergence. Sort of, right? I mean, what do you mean by that? Well, we'll see. I mean, it takes a little bit of doing to talk about that. All right. So that's divergence, and that's all we really need to know at this point. And then the curl. Given a vector field F, we've actually already talked about it, equal to P, Q, R. Define the curl of F is equal to that gradient operator cross F. So that's equal to partial with respect to X, partial with respect to Y, partial with respect to Z, cross P, Q, R. So that's equal to this 3 by 3 determinant I, J, K, partial with respect to X, with respect to Y, with respect to Z, P, Q, R, and what it ends up being is RY minus QZ, and Rx minus PZ negated, so it's PZ minus Rx. And then the last one is Qx minus Py. Like that. Okay? And remember, a 3D vector field, well, so remember vector field F equal to PQR is conservative if and only if the curl of F is equal to 0, 0, 0. So, I mean, in that sense, curl has definitely has some sort of meaning to it, right? It tells us when the vector field is conservative. Let's actually take a look at that. It's actually kind of a nice little calculation. So, for example, given f of x, y, z, right, the curl of the gradient field of f, right, is equal to I, j, k. Well, it's the curl. What's that gradient field again? Let's take a look. So it's the curl of the vector field fx, fy, fz, like that. So this is equal to I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, fx, fy, fz, like that, which is equal to fyz minus fzy, right, which is equal to, in the next component, fxz minus fzx, and in the last component, fyx, fxy, right, which is equal to, for nicely behaved functions f, which pretty much all the functions we look at are, 0, 0, 0, right, by Clairaut's theorem. And the other way around. When you have a vector field and you take the curl and you get 0, then it has to be a gradient vector field. So that was an important property of curl. Although, again, you may be asking, well, what does curl, what does it measure aside from that? And it does measure something. And we'll see what it is in section 6.7 from Stokes' theorem. Anyway, let's do a quick example. The curl of, aside from that one we just did, so we'll say f is equal to, what was that one we were looking at before? Y plus x, 3y minus x. And z squared. So the curl of f is equal to I, j, k, partial with respect to x, with respect to y, with respect to z, y plus x, 3y minus x, z squared. So this is equal to 0 minus 0 in the x component. 0 minus 0. Partial with respect to y is 0, partial with respect to z is 0. In the next component, partial with respect to z is 0, partial with respect to x here is 0. And in the z component, partial with respect to x is minus 1, partial with respect to y, oops, it's 0. I didn't expect it to be conservative, but it is. Let's not actually have it do that. Partial with respect to x is 0, partial with respect to y is 1. So, let's put a squared here. Yeah, partial with respect to 0, partial with respect to y is 2y. So the curl, whereas the divergence is a scalar function, that curl f is another vector field. Curl f is another 3D vector field, starting with one vector field. Also, a two-dimensional vector field, you can always sort of put it in 3 dimensions by making the z-coordinate 0. Given a 2D vector field, right, like this famous one we've been working with, minus yx, we can place it in 3D just by setting z equal to 0 or, some other constant perhaps. So if you have x equal to minus y x 0, now you can take the curl of f. And this is actually not just, a curiosity, this trick. It'll mean something later. I'll show you in a moment. So here the curl of f is I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, minus y, x, 0. So this is equal to, so in the x component, this is 0 minus 0. In the j component, this is 0 minus 0. And in the k component, it's 1 minus 1, which is 2. Right? In general, the curl of a two-dimensional vector field, P, Q, with the r set equal to 0, is going to be equal to 0, 0, just like this one here, qx minus py, where this right, is the expression that's used in Green's theorem. Right, for that two-dimensional vector field, and with the line integral that you're calculating in that vector field, you know, the vector field PQ is transformed into this scalar quantity QX minus PY. And later we'll see in section 6.7 we will study Stokes' theorem, which is a 3D generalization of Green's theorem, as we will see. Okay, so that's all for this section. Just defining curl and divergence and calculating few examples. Okay, so that's the end of the lecture on this section.